Hello and welcome to the podcast. My name is Eleni Wood, and today on Fieldwork Diaries we are joined by Frances Butcher, a PhD student and planetary scientist at the Open University. Thanks for coming along, Frances.
Hello.
So can you tell us a little bit about what it is that you research?
So I study very young water ice glaciers in the mid-latitudes of Mars, and try and find whether they've melted recently or not.
So Mars, this is a little bit different to what we normally have on the podcast because there's some challenges with studying other planets, and particularly if you wanted to do fieldwork. I mean, you can't actually go to Mars. What are the different things that you can do sort of alternatively to fieldwork as we know it on sort of Earth?
So there's lots of ways that we study Mars. Since the 1960s, there have been multiple missions that have gone to the planet. And there's a massive fleet of orbiters going around Mars now. So they take all sorts of data that we can use as scientists back on Earth. We've also got quite a few rovers on the planet. Some of them have stopped giving us data now and are just sitting there, but others are still operating, like Curiosity and Gale Crater. So yeah, there's lots of ways we can study it. And we also go on terrestrial fieldwork to sort of work out processes that could be operating on Mars as well. So.
And glaciers on Mars, I mean, that's not something that many people, well, particularly that I'd heard about before. Yeah. How on earth did we discover the first sort of glaciers on Mars?
So when we look at Mars, we've got really good data. We've got fantastic images of the surface, and we can see features that look very similar to glaciers that you see on Earth. The ones that I look at are long, flowing type features. They're very lobate, very much like a classic glacier that you'd see on Earth. We've also got radar evidence of ice within these features as well. You can see beneath the surface and like layers in the polar caps, for example. So lots of work is going on. There's still debate over whether they're glaciers, but the weight of evidence suggests that they are. So that's really exciting. And obviously we wouldn't know that if we hadn't studied terrestrial glaciers in a lot of detail. So So you can sort of use observations from planet Earth and apply them to Mars, basically. Yeah, you have to be a bit careful because obviously Mars is a different planet, but as humans living on a planet, we have to use the resources that we've got. Yeah. So how did you first get into this kind of area of research? Why are you studying Mars? I like to think of it as studying space glaciers. So as a child, I absolutely loved astronomy. I grew up in the Lake District, and you're blessed living there with very clear skies, very dark skies, where I'd stargaze for hours on end before I could even walk. And also you're surrounded by these landscapes that have been carved out by enormous glaciers. And it was kind of inevitable, really, that I would move into something that combined those two passions. So I realised that I could study the geography of other planets, which blew my mind as a child. So I went to study terrestrial geography at Cambridge, and then specialised in terrestrial glaciology and remote sensing, and then used the independent dissertation component of that to move into planetary science and study past water under the polar caps of Mars. So. That's really exciting stuff. And you were saying sort of remote sensing, so this is what you were talking about with the orbiters. Mm-hmm. Is that something that was developed first sort of for Earth, and then people have taken it to Mars? Yeah, so we've obviously got lots of orbiters going around Earth. You think of Google Earth, you've got lots of images of the surface, and technologies sort of grow in parallel, really. Planetary science is a frontier of technology development that we do also use to develop terrestrial satellites. What kind of resolution do you get when you're taking a picture? Like what can we actually see? I mean, could you see somebody's house? Would that be, if somebody had a house on Mars, would you be able to pick that up? Yeah, so we've got amazing resolution images of the surface of Mars, and terrestrial geographers are absolutely amazed by it. So we've got an orbiter called the Mars Reconnaissance Orbiter, which is a NASA orbiter, and it's produced a global map of images which have 6-meter resolution, and then it also takes absolutely incredible 25 centimeter resolution images.
Wow.
So we can see, for example, the Curiosity rover from orbit. There's no hiding on Mars nowadays.
No.
So imagine an average-sized person laying down on the surface. You would be able to see at least evidence that they're there.
Yeah.
So
you
it's
wouldn't
amazing.
see their features, but you'd be able to definitely point out a person.
And you can use those very high-resolution images to make 3D models of the surface. So I've got in my office right now a 3D model of the surface of Mars, or a portion of it at least, at 1 meter resolution. So
that's incredible.
That's really rivaling the Earth data sets. And of course, all this data is free as well. That's a real benefit.
Anybody could go on and have access to it and fly themselves around the surface of Mars.
It's all freely available on the internet. And the really good thing that space agencies are doing is engaging the public to use this data, because it gives a completely different perspective.
So, as well as being able to create these amazing topographic models and stuff, and when you spot things on Mars, you can compare it to Earth. So, what kind of fieldwork is really useful, sort of back here on planet Earth? I mean, like, do we have many analogues for Mars that we're looking at today?
Yeah, so the main analogue for the glaciers I study is actually in Antarctica, in the dry valleys. They're debris-covered glaciers, quite difficult to get to, but the really great thing about planetary science is that we are using remote sensing technologies that are also applied on Earth. So they're sort of growing in parallel, such that terrestrial geomorphologists are now using remote sensing data sets to collect big data sets of Earth landforms. So I compare landforms on Earth to those on Mars using these big data sets. Of course, going into the field is also very important. You can't ever replace fieldwork. And the thing I find really useful about fieldwork is that when you're looking at an image with 25 centimetre resolution, it feels very high resolution when you're looking at it, but you can very easily forget that something that looks very smooth on the surface of Mars could actually be composed of rocks that are half the size of a human being. So going into the field and seeing a landform and realising that the things that make up that landform below the resolution of the data you're using is really important, because then you understand the limitations of the data you've got. And that's an essential experience for any planetary scientist, I think.
Yeah, so you're basically looking at something that you're missing a portion of that kind of finer detail, and you could miss sort of important features that are hiding under that kind of lower resolution.
Yeah, and of course we've got rovers on the surface, which are basically doing what a geologist would do, albeit at a slightly slower timescale. And that gives very local, very, very high resolution data. But obviously that's very localized. You can't do that for the whole of Mars at the moment. So
so do you think that the future of kind of Mars fieldwork is going to be more rovers to add to that kind of fine detail that we're missing from the satellite imagery?
Yeah, so rovers are really important, and they give us really insightful ideas about the very local geologic history. A real challenge that we have at the moment is that from orbit we can't work out how old things are. We have techniques that allow us to work out the relative ages of things based on what's overlapping what, or how many craters are on a surface. So we crater count a surface, and the number of craters or the size of craters tells you how old it is. But you can't replace lab experiments where on Earth you would date a sample with very
you'd be able
techniques.
to bring your rocks home, and you'd be able to use other techniques to date them, I guess.
So I think there's a lot of potential for rovers to do that. The real future for Mars science at the moment, in terms of rovers, is probably sample return. Sending the Mars 2020 rover with NASA is going to land on the surface of Mars and take samples and cache them on the surface that a future robot will then go and pick up and hopefully send back.
Oh, wow. So we're going to have rockets taking off from Mars back to Earth, maybe.
Well, they're not finalised yet, but I think the plan is for that to happen.
That's really exciting.
Yeah.
Yeah. So you've been involved, haven't you, with some testing of rovers?
Yes.
Yeah. So that was involved with the UK Space Agency, wasn't it?
Yeah. So we recently had the first Mars-Utah rover field investigation, which is affectionately known as Murphy, and it was basically an exercise to train UK planetary scientists in how you operate a rover on a planet that's 200 million kilometres away. So the basic principle was it's best to make mistakes on Earth before you make them on Mars with a very precious and expensive robot. So
Makes sense.
we were preparing for the ExoMars mission, which is a European Space Agency and Russian Space Agency mission, which is going to Mars to drill into the subsurface in 2020. And it's basically looking for signs of ancient life. So we decided to simulate a mission on Earth, which was going to search for ancient life in Utah. So basically we had two teams. We had a field team and a remote operations team. So the field team went to Utah with a rover. It was a site that looked a lot like Mars. There was nobody for many, many miles. And then the team in the operations centre controlled the rover as if it was on Mars. So we had minimal interaction between the teams. And that really allowed us to sort of get into the mindset that we were operating a very important, precious rover.
Yeah.
So each morning we would wake up in the UK, we would get data down from the rover, for example, where it had landed. And then we would look at the data for about an hour, as they would on a real Mars rover, and then decide on science targets that we wanted to look at. We'd upload that to the field team. Then they would upload the commands to the rover, send it off on its work, and then in the afternoon, while the rover was doing that in Utah, we would be looking at the previous day's data to sort of delve into the science a bit more.
Sure.
And then by the end of the day, the rover then uploaded the data back to us in the UK, and then the next morning it was ready for us to do the whole thing again. And that was a really interesting exercise, actually.
Yeah,
so that's amazing.
So that's exactly how it would work, I guess, with Mars, because you've got such a long time between communications with the rover. I mean, how long does it take to communicate with a rover?
I think it's about 7 minutes time delay.
Okay, that's not as long as I thought it would be.
Obviously, you have to upload commands as a group of commands.
Yeah. With the experiment in Utah, what kinds of data were you asking the rover to collect?
So we had a rover platform that's been developed in the UK by UK scientists, and it's got emulator instruments that are similar to what we expect to go on the ExoMars rover. So there were panoramic cameras, we had high resolution cameras, and also some, I think we had some spectrometer instruments as well, and we also had a drill.
Okay, so you can take samples from the surface. And
so we performed one drill during the mission to delve down into the subsurface.
Yeah.
And we've cached some samples of that for future analysis. So
yeah, I guess that when you're operating a rover, you are having to be very careful what you choose to do with it, especially I guess with drilling. Like I mean that seems like an operation that you might damage it, and if it's on Mars, I mean there's nothing that you can do to
absolutely
to
the
fix
drill
it.
is an absolutely critical part of the mission, and on ExoMars it's going to be a fixed drill, so it's really important that you maintain that. So if you're working on Mars, you're going to have weeks to months of planning before you perform a drill.
Yeah.
Our simulations are only a couple of weeks long, but hopefully reconstructed the process quite well.
Yeah, that's really cool. And would you ever go to Mars yourself if they were?
I don't think I'm brave enough, but I'd love to. Obviously, I'd love to immerse myself in the landscape. It feels like home. I stare at it every day on the computer screen, but to be honest, it feels like quite an uncomfortable place to be. I'm quite cozy on Earth.
Yeah, I mean, other than the glaciers and the craters that you were talking about, are there any sort of other interesting features that you've spotted yourself on Mars that people wouldn't necessarily know are there?
So, in terms of not the glaciers themselves, but in the forelands of the glaciers, as part of my PhD project, I've been looking at what are called eskers. So these are ridges of sediment that have been laid down by glacial meltwater. And previously, it's been noted that there are very ancient eskers near the Mars South Pole, associated with the polar cap, which formed when probably when the atmosphere was thicker, and it was more conceivable that we would have a warmer climate. Maybe not a warm climate, but warmer than it is now.
So you'd see melting of your glaciers because of
the South Polar Cap.
Yeah.
What's really surprising is that we've seen eskers associated with very few, but at least some very young glaciers on Mars.
Okay.
And these are glaciers that have always been thought to be frozen to their beds. They've thought to have never produced meltwater.
Okay.
So the fact that we've seen these
That's really
eskers,
interesting.
or possible eskers, is really exciting.
So that means that we might have liquid water on Mars at the base of these glaciers?
Probably not in the present day.
Okay,
but
recently?
When I say recently, within the last maybe few 100 million years which is very recent on Mars.
Yeah, geologically that is recent.
Yes. And that obviously has really important implications for searching for life, because subglacial environments are protected from the atmosphere. And on Mars you have a lot of UV radiation, which is very harmful to life. So subglacial environments are thought to be very good candidates for searching for life. So if you have an esker which formed in a subglacial drainage system that's been exposed in the landscape, that's something you can go and poke with a rover possibly, and search for life without having to drill down through ice.
So you might have it just lying at the surface, ready to be found.
Possibly just beneath the surface, because
the surface.
UV obviously
has killed,
may have damaged. But it probably, it's exciting, but distant.
So are there any real limitations at the moment? I mean, we've talked a lot about kind of where the science is going and all of the new developments, but do you foresee there being like any major limitations on the way we study other planets?
There are three main things that crop up for me. The first is that obviously getting to Mars is very difficult, so it takes decades to plan for missions to send. It's very expensive to go there. So we have to sort of think of inventive techniques to apply to the current data. And we're very blessed to have amazing founts of data coming from Mars at the moment. The second is that we do have Martian rocks on Earth, and they are in the form of meteorites. They've been kicked out of the Martian environment, for example, by an impact, and they've travelled through space and landed on Earth. So we are getting insights into the Martian environment. However, they're completely stripped of their geological context. Mars has got a very diverse surface.
Okay.
Where did that rock come from on the surface? That's really important as a geologist. You go into the field, you pick up a sample and you study the area around it. So obviously that is quite a limitation to understanding actually the environment that those rocks formed in, hence the importance of sample return in the future. You also have other challenges on Mars in terms of remembering that it's not Earth. So on Mars, we don't only have water or water ice or a water cycle, water vapour operating as a geomorphic agent. We've also had carbon dioxide, because the atmosphere is primarily carbon dioxide on Mars, it's not moist like the terrestrial atmosphere.
Okay.
And that means that we could be looking at morphologies that have developed by carbon dioxide rather than water flow.
Liquid carbon dioxide flowing around on the surface.
Or gaseous
carbon
dioxide. Yeah. So the polar caps, for example, have carbon dioxide ice in them. And that's a massive challenge for a glaciologist.
Yeah.
Like, how do you work out how water and carbon dioxide ice are interacting?
Okay. Is that something that people have tried to model and look at, I guess? Or
so there is a lot of work going on the South Polar Cap, for example, and I'm actually applying a model that was developed based on terrestrial glaciers to mid-latitude regions on Mars. I'm yet to work out how to incorporate carbon dioxide into that if I need to.
Yeah. So I guess what you're doing is you're putting together your own glacier and then trying to build the features that you see on the surface of Mars. Is that the idea?
The model that I use, effectively you say you have this much ice being deposited on the surface. These are the environmental conditions, so temperature and geothermal heat, for example. And then based on terrestrial glaciological theory, it builds over a period of time a glacier. You've got this
Okay,
glacier
so
sitting on the surface.
you're
and then
growing
you can, growing an ice sheet on Mars, basically. And then you can work out, based on theory, what, for example, the temperature would be at the bed, in order to try and work out, therefore, if a glacier under these conditions may have produced meltwater that could have produced the features that I'm looking at.
Yeah.
Obviously, numerical models have limitations. You can never replace geological observations.
No.
But they're a useful guide.
Yeah.
Yeah.
Is there any funny stories that have come out of your forays into Martian research?
I think some of the stories that came back from the Murphy field trials were quite amusing, hearing about how, so sitting in the operations centre, we weren't aware of the people standing around the rover. And when they set it off in the morning, they had to leg it out of the way very quickly before the rover caught them in shot and got a picture of them in the field site. So they would have to duck behind rocks and try not to be seen. It was playing a spot the geologist in the pictures. But they did a very good job. We couldn't see them. It was excellent. Yeah.
And one of the questions that we always ask is there a piece of field equipment that you wouldn't be without?
I'm very, very closely attached to my dry bags, ideally colour-coded dry bags, because I don't like the feeling of putting soggy socks on at the end of a long day of field work.
I don't think anyone does.
Yeah, dry bags are my essential, apart from my camera and my GPS maybe.
And do you have any advice for any budding planetary scientists or people who are just really interested in this? Like, what would you suggest that they go and look at or do?
As I said, the great thing about planetary science data is that it's all available on the internet. You can see Mars data in Google Earth, for example. A lot of people don't know that, but it's there sitting ready for you to explore. And just throw yourself in, really. It's very easy to think that all of the planetary science goes on in the States with NASA, but there's a very vibrant planetary science community here in the UK that are very welcoming to newcomers. That's how I got into it. Everyone was very encouraging. So if you want to do it, it's perfectly possible to do so.
Just go for it.
Yeah, go for it. Yeah.
Oh, that's fantastic. And if people wanted to find out a little bit more about your research, where should they go and have a look?
I do have Twitter, so follow me on Twitter. My handle is @FEGButcher. And there's also lots of websites on the internet with people getting very excited about planetary science because all the data is available to them. So lots of places. Just Google it. Yeah.
So go check Frances out and all of her exciting Martian fieldwork and glaciology. So it's been absolutely fantastic to have you on the podcast today, Frances. Really, really fascinating stuff. I think I'm going to be getting on the internet and finding myself some Martian images to have a look around. Thank you, everyone, for listening today. This has been the Fieldwork Diaries, and we've been hearing from Frances Butcher. She is a PhD student and planetary scientist at the Open University. We hope that you've enjoyed listening, and join us next time for more exciting fieldwork stories. My name's Eleni Wood. See you next time. Fieldwork Diaries is produced at the Open University, and it wouldn't be possible without the amazing people behind the scenes. Music was written and recorded by the wonderful Matt Kent, and fellow fieldwork and podcast enthusiast Stacey Phillips has made us a beautiful website at fieldworkdiaries.com. Check out our Twitter @Fieldwork Diary and Instagram Fieldwork Diaries for live updates. Thanks again for listening.